Hello, I think you can hear me now and should see the desktop. Does everything seem okay?
Yeah.
Okay,
Yes.
great. Thank you. Okay. Okay. So today we're going to talk one more day about C, and we're trying to try to cover the ideas in C that are needed most for for the programming assignments, not just the one we're doing now, but the ones we'll be doing later in the semester too. What I did here is I put links to all the readings we've had about C, the most important ideas. Okay, so what we're going to be talking about today is again is pointers, arrays, struts. This is from one of the books. Okay, there's pointers, arrays, struts, and then here's pointers, arrays, struts again from a different book. If you like one more than the other, they explain things pretty similarly, though they give different examples. So if you feel comfortable with it, you can skim these ideas. You don't have to skim both of them, but it's two different. It's complicated enough that sometimes reading more than one explanation is useful. But see, notice it's pointers, arrays, struts, pointers, arrays, struts, pointers and struts, arrays of struts. So there's variations on the site ideas. And in this section on pointers, it's important, especially pointers and functions. And in this section on arrays, arrays and functions. And this section on struts, struts and functions. So you can see that they make a little bit of a special emphasis. And that's what we're going to be talking about today is how these things interact mostly with functions. So these are the kind of ideas that we need to really understand. And then there's one more reading that's a new one, this one here. It's a very good explanation of memory management. Okay, something that you don't really pay attention to in Java, but you have to pay a huge amount of attention to in C and C++. And this is where the visualizer comes in. It draws pictures of the memory management for us. And what's nice about this is a book that's called C for Java Programmers. And what I like about it is that it contrasts them. Okay, so it's here. Here where it talks about memory allocation, it's always comparing C and Java. So dynamic memory allocation in Java and dynamic memory allocation in C. It's constantly comparing them. So it's very useful for you to see how the two languages compare. Maybe you should be more familiar with Java than you are with C at this point. So being reminded of exactly how Java does things and then seeing how C does it differently is a good way to understand this. And uh, the languages look a lot alike when you look at the code, but you have to realize that they act quite a bit differently. We saw a little bit of that last week. We saw that if you just set x equal y, that can mean something very different in Java than it does in C. And that's what we're going to go back to is simple things like what does x equal y mean? Okay. Now, remember we talked about this idea last week. Here, x equal y. That's we call that assignment. Okay. Here, y is x, y is 8, x equals y. So you pretty much know what x is. X is 8. But what if y not is a simple thing, but what if y is a composite type? In the case of Java, what if it's a strut? Okay. In the case of C, again, you get these problems with, what do you really mean by this? Okay. Now, why that's so important is function parameter passing is a form of assignment. Okay. When you define a function, then you call the function, you're essentially saying that the parameter equals the argument. Okay. You're assigning the argument to the parameter. You're assigning the argument to the parameter. So essentially it's this. Okay. You're assigning the argument to the parameter. And that's how most languages look at it. They treat parameter passing in functions as a special case of assignment. So then you have to ask, well, what do they mean by assignment? C and Java have very different ideas of assignment. So they end up with very different ideas of parameter passing. And this is where things get difficult. You have to understand what functions are doing. Okay, so a real simple way to approach this is we want to know what assignment does. That'll help us understand what parameter passing does. What assignment does depends on what you're assigning. Okay, in Java, let's see. in Java, we only have two kinds of variables to worry about. We have primitive variables and we have reference variables. Okay. And what assignment means something for each, when you say x equal y, if x and y are primitives, that's different than saying x equal y when they're reference variables. Okay, x equal y has a different meaning for primitive variables and for reference variables. Okay, now C is a much more complicated language. In C, we got a lot of variables to worry about. Okay, so in C, we can worry about well, they don't use the word primitive, but it's not a bad word. So primitive variables like int, double, okay. And then they have uh, array variables and strut variables and string variables. Well, let me put string under array. Strings are a special case of array, but they're not quite the same thing. So in C, you got to pay attention to how strings are handled. So you've got array variables and string variables, and string variables are a kind of array, but they have special rules that arrays don't have. Then there's strut variables, and then you have pointer variables. Okay, so you end up with 5 kinds of variables. Okay, that's a lot, and they all have slightly different rules. You know, if you start doing x equal y for these guys, things that x equal, if you have a primitive variable here and a primitive variable, if you have x and y are primitive variables, then that pretty much means the same thing as it does in Java. Okay, but when you have arrays or strings or struts or pointers, then you have to really ask, what does x equal y mean? Okay. For arrays and strings, it pretty much means the same thing. In that case, they're pretty close to being the same thing. For struts, that's where things really change. Struts in C act kind of more like primitives. Okay. Struts act more like primitives. Arrays in C act more like Java's reference variables. But that's not 100% true. But in Java, C arrays okay, this is roughly what it is. C arrays are kind of like Java reference variables. Okay, struts are kind of like Java or C primitive variables. Okay, and pointers are it's hard. Pointers are kind of like C reference variable, like Java reference variables, but that's actually kind of in a sense you could say, but yeah, you can kind of say that C pointers are kind of like Java reference variables. Okay, so it's a little bit tricky. In a sense, what Java did was they said, let's boil it down to two things, and what are the two most important things? And they came up with primitive and reference. C had a whole variety of things, and when the Java people looked at C, they boiled down all of this kind of to these two ideas, because arrays were kind of like Java reference variables. Okay. Yeah, arrays were kind of like Java reference variables. Struts, they got rid of this. Essentially, they got rid of this entirely. Struts kind of like primitive variables. That the Java people decided that was not useful. So they got kind of rid of that. Okay. All right. So what we're going to do today is look at more examples of C like we were doing with a visualizer, like we did in class on last week, and we want to see how these things interact with parameter passing. Okay, we want to see how assignment how parameter passing acts like assignment. Okay, last week we only looked at assignment. We only looked at assignment. Now we want to look at parameter passing the way it looks like assignment. Okay, let me save this. Okay, now the code we want to look at is in this zip file, and then today we're going to look at something code that's in the zip file. Okay, this new zip file is really kind of just another way to look at what's in this previous zip file. Okay, so there's this new zip file on data structures and functions. Okay, it's just another way of presenting some of the examples from working with composite data types. There's nothing new in it, but it's just another way of explaining the same, of showing slightly different examples showing the same thing. Okay, so let's start with this one. Okay, we did these examples last week. Simple example and simple strut example. Okay, and if I open them, the key was that line of code there versus that line of code there. So line 23, line 23. Those equal signs didn't mean the same thing. Okay, and this is real important. Those equal signs didn't do the same thing there and there. Okay, if you copy this again real quick, just put this up on the Java visualizer. That one line of code, this one here, is really the key, because that's going to show us, since the assignment didn't act the same in Java as it did in C, that gives us a hint that functions aren't going to act the same in Java as they do in C. Okay, what happened here? Whoops. Oh, I forgot I forgot to copy one of the braces. Okay, if we get down to that line, okay. Oh, I passed it. Okay, S3 equals S2. Okay, it made two references point to the same object. Okay, so that line of code made two references point to the same object. We only have one object, but we have a bunch of reference variables. This reference variable ended up pointing at this object, this reference variable pointing at the same object. Okay, but line 18 made two reference variables point to the same object. Okay, now let's look at the same line in C. Okay, so to get to the same, let's take this and put it in the C tutorial, in the C visualizer. Oh, I hope it wakes up. Okay, good. It got through. Okay, now we want to get to line 18. Okay, what's S3 equal S2 going to do? Well, down here you see that S2 is this strut and S3 is this strut. And what you do is you copy that strut into that strut. Okay, S2 was a reference. Notice that when I say S2 is this example object, S2 points at the object in the heap. When I say that S2 is this object, S2 is that object. See, it's like a primitive variable. When I mentioned that struts are kind of like primitives, when you say that S2 is this object, S2 is that object. There's nothing in the heap, okay? But when you say in Java that S2 is that object, you really mean that S2 points at it. Then when you say that S3 equals S2, this is just another reference variable, so it's another pointer at the same object. Here, when you say that S3 is S2, well, S3 is its own object, so then you have to copy what's in S2 into S3. So I've got two objects. I've got an object S2 and an object S3, okay? And then over here, I have one object, but two reference variables to it, okay? And then over here, I get another reference variable, okay? Over here in the C version, I purposely created something like a reference variable, but I do it explicitly. I say S4 is a pointer to a strut. So now I get something pointing at this strut. So here I naturally got pointers. Here I have to ask for pointers. So I have to ask for a pointer. Okay. So if I want C to act like Java and get references, if I want, because we don't call them point references, we call them pointers in C. If I want pointers, I have to ask for them. In Java, you get pointers or references automatically because you either have a reference variable or you have a primitive variable. All objects, their variables are references. Objects always have arrows pointing at them. You can't have an object on the left-hand side of this picture. It's impossible in Java. You can't have this object sitting over here. Java, in C, you can. Okay. And in C, I can get the object over here, but I have to ask for it. See, I had to ask for the object to be over here. In Java, you get the object in the heap automatically. You can't get it anywhere but in the heap. Okay? So in Java, objects must be in the heap and variables must point at them. In C, you have all these choices. The object can be in the variable or the object can be in the heap. You could have a pointer to the object or you could have the object, the variable be the object. See, the variable can be the object or the variable can point at the object. The object can be in the stack or the object can be in the heap. So in C, you have to explicitly say, I want a pointer. I want the object in the stack. I want the object in the stack. I want the object in the heap. I want a variable that is an object. I want a variable that points to an object. Okay. I want a variable that is an object. I want a variable that points to an object. I want an object in the heap. I want an object in the stack. So we have slightly different ways of saying all these things. Okay. So it's real important to keep that in mind. Notice that that line of code meant something very differently than that line of code. X equal Y you don't know what X equal Y means until you ask, what language am I in and what is the type of X and Y? Okay, the simplest thing you can write, X equal Y, you don't know what it means until you ask, which language am I in and what is the type of X and Y? Okay, so in Java, X equal Y, when they're reference variable, copied pointers. In C, if X and Y are struts, X equal Y acts like primitive. It just copied one strut into another strut. It just acted like, again, it acted like it was a primitive, like it was just an int or a double. It copied this guy to there, it copied this to there, and it copied this to there. Okay. All right. Now, let's go and start asking what happens when we make things more complicated by introducing functions. Okay. That's these examples down here. Okay. There was no functions in these examples. There were no functions. We haven't done we're going to skip the one on strings. Okay, for now, you can look at that one, but no, those examples only create variables and do assignment. They don't do any function calls. So these examples down here start adding function calls to it. Okay, so let's see. So let's look at the Java one first. It's important to go back to Java because it's your base case. It's the case that you want to say, okay, when I'm working with C, how is it different than Java? Because you have to think differently when you're writing C code. If you're thinking if you think C works like Java, your code will be mysterious and you won't understand it and it'll be buggy. So you kind of have to know exactly what Java is doing so you can see how you have to realize where C is going to do it differently. Okay, so here is an object that has an int, double, and a char in it. Okay, well, this is the same object we looked at earlier. But now we're going to have functions that take objects as input. See, there's a function. It takes an object as an input. But what does that mean? It means that it takes a reference variable to the object. The objects are going to be pointed at in the heap. Okay, so let's put this in the Java visualizer and just visualize it. Okay, all right. So no variables yet. We're starting in main. Well, actually, we have a global variable. We have a static variable. So we start with building the static variable. So the first thing we do is we instantiate the static object, the global object. Okay, so step through the code. Okay, so there's that static object. Now we're in main. So we initialize the static object and then we enter main. So notice that this constructor got called. This constructor got called before main did, which is something that people don't realize sometimes in Java. They think, oh, your program starts in main. Maybe not. In this case, the program actually started in a constructor of an object because it had to initialize the static variable before it could even enter main. Okay, so that's kind of your program didn't start in main. The program started in a constructor. Okay, that doesn't happen in C. In C, for example, programs always start in main. Okay, because C treats things just a little bit differently. But in Java, your program can start in a constructor. Okay, now we are in main. Okay, and now we're going to create. We got one object sitting in the heap, but it's a global object. Okay, now we're going to get two more objects. Okay, so S2 and S3. Notice that all the objects are in the heap, and the reference variables are they're local. The reference variables are local variables. The objects are in the heap, and all the variables are essentially what C calls pointers. Okay. Now we're going to call the function. Okay. The function has parameters. What gets passed? What gets passed from here to here? Okay. This is like assignment. This actually is a version of that. Okay. See, I'm assigning S2 to S3. And we knew that just copied an arrow. Now we're calling F with that parameter. So S2 is being assigned to S1, this S1. And this S3 is being assigned to this S2. So I'm writing S1 equals S2 and S2 here equals S3. But like I did over here, it's just going to copy arrows. See, S1, that arrow got copied into there. And that arrow got copied into there. Just like over here, we copied an arrow from here to here. Now we copied an arrow from main's local variable to the function's local variable. We copied that arrow to that. From that local variable, that arrow was copied to there. And from that local variable, that arrow was copied to that local variable. No new objects. Okay. Just like assignment here didn't create new objects, just created more reference variables. Assignment doesn't create another object. That also means that if this function manipulates that object is manipulated in main also. See, now we're in the function. If that function does anything to the object, then when the function touches this object and changes it, that object's been changed when you get back into main. And that's important. The functions, since they're given references to the object, they can look inside the object, make changes. So we have a name for that. What does that mean? Think about it. We talked about that earlier in the semester. What does that make a reference variable? The function takes these guys in. The function can reach inside there and make changes. We gave a name to that earlier. What does it mean for a function? What is the purpose of a function? Why do you call functions?
To perform an action with some data.
There's actually two. You can perform an action with data, or you could do it for what reason? There's two slightly different points of view. Why do you call the logarithm function? Why do you call the cosine function? Why do you call the exponential function?
Perform that function on an integer?
No. Why would you press the exponential button on your calculator? What would be your purpose for doing that? Why would you press the logarithm button on a calculator? What would be the purpose of pressing that button? For what reason?
To find the output that
To get the
you want.
output. Yeah, like I say, to get the output of the function, right? To get the return value, get its answer. Now think of it. Why do you call the print function? Is it to get back its answer?
No.
No. You call the print function why? Like what was the first person? You call the print function for what?
To output to the user.
But think of the language. What the first person said. You call the print function, to do what? No, I remember who was your first answer. You call a function for what reason?
To perform an action.
Right, and that's what print does. What action does it perform?
It prints.
It prints. Yeah, it performs an action. What answer does it give you back?
Whatever you feed to it.
No. Think of it.
Doesn't really give you an answer.
It doesn't give you an answer. Look, system.outprintf. There's no answer. There's no return value. It's only called to do something. It's not called to give you back an answer. On the other hand, the exponential function, you just call it exactly for the reason of getting back an answer. So some functions are called for their action, and some functions are called for their result. That's hugely important. Some functions are called for their action. We call that a side effect. And some functions are called for their result. Okay. Now, one of the first things we talked about in the semester was this idea of in, out, and out variables. In, out, and out variables. What was that about? What were we talking about? In, out, and out. Remember, I've used these terms. I've used these terms a lot of times, and I'm going to keep using them because this is the language of programming. Like in the homework assignment, you have to learn about create process. And I've told you that is a out parameter and that's an in parameter. I'm sorry, the other way around. That's an in parameter, that's an out parameter. And later on, we'll see in out parameters. What's that mean? What do you mean in parameter, out parameter? You can't write C code unless you know what this stuff means. What do I mean by an out parameter? That guy's an out parameter. Okay.
It's a return value.
Nope. This function's return value is over here. The function's return value is a Boolean. So yeah, you're on, but so what do we mean by that's an out parameter? That's the return value. Over here, printf doesn't have a return value. This function does have a return value. So return value is when you get a result back. Okay. This function has a return value that's a Boolean, but this is an out parameter.
It's a kind of return value. Doesn't it like change data elsewhere?
So this thing points at a piece of data, and the function does what?
Changes that data?
Yeah, it changes what the function, yeah, this thing points at data and this thing changes what's in it. That's exactly what we're talking about over here. I'm sorry. See, that's exactly what I'm talking about here. This function, this parameter to the function points at that data. The function can manipulate that data. If the function manipulates that data, then this becomes what?
An out parameter?
Well, because the calling function would see the changes. See, the calling function is pointing at that object. The function, if it changes that object, when the function returns, the calling function sees the changes. That's an out parameter. In Java, every reference variable is an out parameter. In Java, every function with a reference variable is an out parameter automatically. Okay, because the calling function can reach inside of the object, make changes, then those changes show up in the calling function. Main will see the changes that the f made. If you call f, pass it a reference to an object, f can manipulate what's inside the object, so when f returns, you see the changes in the object. That's a out parameter. All reference parameters in Java are actually out parameters because the function can manipulate what the thing is pointing at. Okay. If you don't want that to happen, then you have to start using the constants, the keyword. Like in your Java code, you can go over here to the Java code, and then we're not going to need this, but in Java code, you can do that means you can't make changes to that object. Okay, but kind of. You have to be real careful about this. But there's the final keyword, which is a way of saying this thing's an out parameter, but I don't want it to be an out parameter. I don't want you to be able to change it. So you have to use the final keyword if you want to say, but I don't want there be any changes made to the object. Okay, because as we see in this picture, once the function's got a pointer to the object, it could start making changes in there. So there are ways to stop the changes from happening, and you have to use the final keyword for that purpose. Okay, all right. So in Java, when you pass a parameter like this, if it's a reference variable, you're getting a pointer to the object, so it's actually an out parameter. Okay, because it's acting like this assignment did. This assignment created multiple references to the same object. So parameter passing creates multiple references to the same object. We now have two references to that object. One reference was our variable. One reference was this variable. Then the other reference is the parameter in the function call. The parameter is now a reference variable to that object. Okay, so parameter passing acts like assignment. Okay. Now, what about in the C? Let's look at the C version of the same thing. Okay, what happened in the C version of this? Okay. Okay, let's go back to the folder. Okay, so this was the Java version. Okay, here's the C version. This is one of the C versions. Unfortunately, see in Java, when you work with objects, you just only have to worry about objects. In C, you have to worry about arrays, strings, and struts because they're all slightly different. So arrays in Java are objects, strings in Java are objects, and classes in object are objects. So in Java, there's only objects to worry about, reference variables. In C, we got all of these. The closest one to Java's objects is struts. Well, not, well, kind of up close. Okay, so okay, now here's the more or less equivalent C program. See, the Java program started out by creating a class, which is a strut. The C program starts out by creating a strut. See, and the strut holds an int, a double, and a char. Here it holds an int, a double, and a char. Here's a global strut. Here's a global one. Okay. Then we go to, here's a function definition. Here's a function definition. The function takes in 2 examples. Here, the function takes in 2 example struts. Okay. Then it does pretty much the same thing. The code here is pretty much exactly the same thing as the code here. Okay. Then the main method creates 2 local examples. Here, the main method creates 2 local examples, and then it calls the function. Okay. And here, it makes 2 local variables, and then it calls the function. Okay. Now, here we saw that the function parameters acted like out parameters because you actually, these were created in the stack, in the heap. Then you passed a pointer to them, to the function. So the function's parameters are pointing at the objects in the heap. Okay, they're pointing at the objects in the heap. Okay, see the function's parameters. Okay, let me close the ones we're not using anymore. The function's parameters are pointing to the objects in the heap. Okay, now look at the C version. And it's not going to act like the Java version. Even though the code was written to look as much like Java as possible, the Java code and the C code are written in parallel as much as possible. Other than little syntax changes, they're essentially the same program, but they don't act the same way. Okay, so when this one starts up, the C visualizer is much slower than the Java visualizer. Remember the Java one, just review, when it started up, well, at first it created the global object. Then you went into main and created the 2 local objects. But the local objects, what's local are the reference variables. The objects are actually in the heap. Okay, real important. The objects themselves are in the heap. That put the objects in the heap, that's the local reference variable. Okay, over here, okay, now notice we start in main. Okay, the global variable was already built for us. It's actually built by the compiler. It's not built at runtime, it's built at compile time. In the Java case, you actually had to start in the constructor at runtime to construct the global object. In the case of C, the global object's sitting there already. It was put there by the compiler. It's not built at runtime, it's built at compile time. Okay, that's a minor difference. So the program actually starts right in main. Okay, and actually right away you see something. S2 and S3 are not in the heap. They're in the local variables. The local variable S2 is the object. The local variable S3 is the object. Very different than Java. In Java, the local variable S2 is a pointer to the object in the heap. S3 is a pointer to the object in the heap. Okay? That means that when we do parameter passing, something has to be really very different because here we passed pointers. So what are we going to do here? Okay, now the first thing you have to do is initialize these. Notice that they're in the variables are there, but they haven't been initialized yet. So line 49 initializes one of them, then line 50 initializes the other. Okay, now we call the function. Okay, this is where things get real interesting. We're going to, just like we go back here to the very first line of the function. Okay, so here we're about to call the function. Here we're about to call the function. Okay, when we call the function in Java, we create the function's local variables. Whoops. Okay, there we're about to call the function. Okay, we create the function's local variables and copy these arrows into the local variables. So we just called the function. See, we just came from the function call. That's the gray line, and we're over here. So we created these local variables in the function that point at those objects. In C, when we call the function, something entirely different happens. The function doesn't have, the function's local variables are the objects. That object got copied into that object, and that object got copied into that object. Okay? All right? So it copied the objects. Okay. Now, what difference does that make? Is that a big deal? Does that matter to us? Okay, think. So this F has got copies of those arguments. This F has got pointers to those arguments. Is that a big deal or not?
Yeah,
Why?
because if it's the pointer to the object, then we can change the object in the method.
Well,
If it's
no,
just
I
a
think
copy, we can't change it.
you're fading out. We can't hear you.
If it's just a reference to the object, like we copy the object, then we can't change the object in the method. But if we have a pointer to the object in the heap, then we can actually change the object.
Yeah, exactly. See, these are inherently what we call them what? If you've got pointers to the object, the arguments are actually what?
References.
They're references, but what's special about them? If the function's got references to these objects, like he said, what can the function do?
Edit them.
Edit them, change them. Then we call that what?
Passing by reference.
No, what did we just call it a minute ago?
Out parameter.
An out reference. You can use it to pass information back to the caller. Okay, in Java, every reference parameter is actually an out parameter. Now, what about in C? Suppose the function changes that object.
S1 and S2 in main won't be changed.
No, there's not going to be any copying back to these guys. Nothing's going to be copied back to them. So changes to these doesn't change these. So what kind of parameters are these then?
In parameters.
Oh, yeah, they're in parameters, not out parameters. By default in C, struts are in parameters, but in Java, they're by default out parameters. That's very important. That's a real important thing to remember about these languages, that in Java, since you're passing references to the objects, you can always reach inside the objects and update them and change them. So then every reference variable becomes an out parameter to a function. In C, the natural way to do things is that you copy the struts. The struts are see, and it's this assignment. When we saw a minute ago, the assignment in Java, or the assignment in C of reference variable copies struts. The assignment of reference variables in Java copies arrows. In Java, you copy arrows. In C, you copy struts. If you want to copy arrows in C, you have to explicitly use pointers. And then you can actually copy arrows like Java does, but you have to do it explicitly. Okay. So now the function's working with these copies of these parameters. Okay. So now it doesn't matter what the function does to those. It doesn't matter what the function does to the copies. It can't make changes to them. Okay. Now let's go back a few steps. Okay. Okay. So here we're about to call F. Okay. When we call F, that's when we get these copies. Okay. We get the copies when we call F. Okay. Now F does its work. Now F returns. Okay. Now we're going to call F again. Now notice when I call F again, I'm using S3. Okay. So it's going to copy S3 into one of F's parameters. And then I use a strut literal. This is a strut literal. So the other parameter to f is going to be 4, 3, 2, 1. One of the parameters is going to be 5, 6, 7, 8. The other is going to be 4. So this is just an example of a strut literal. Java doesn't have object literals, but C has strut literals. So when I go down here, see, one of the parameters was 4, 3, 2, 4, 3.21, and the other is 5, 6.78. So the first parameter was a copy of this literal strut. Where was it? Oh, the first parameter is a copy of this literal strut. The second parameter is a copy of that object there. Okay, right. So now we return. Okay. Now I'm going to create an object in the heap. Okay, so now I've got an object in the heap. Now I put something in it. Okay, so now I filled it in, I've initialized it. So that, remember, when you create an object in the heap, there are no constructors in C. So when you create an object, it's always uninitialized. C has no constructors. So when you create an object in the heap, you then have to have code that explicitly fills it in. This is real important. C objects are always malloc uninitialized. In Java, you always have a constructor that fills in the object for you. That you don't have anything like that in C. So every time you malloc something, you better start thinking, how am I going to make sure there's valid data in it? You have to put the data in it yourself. So here we initialize it step by step. Okay. Now I'm going to call this function. Okay. And this is real interesting. I'm going to call the function with parameter S1. Well, S1 is this object here. That's going to get copied into the first parameter of F. What about the second parameter of F? Well, S4 points at that object. I dereference S4, so I'm pointing at that object. But parameter passing of struts is by copying them. So this object's going to get copied into the new function. So the new function is going to make a copy of S3 and a copy of this guy from the heap. So this is going to get copied from the heap into the stack. So make the function call. I have to scroll back up and down. That thing got copied into there. Okay. And this global one got copied into there. So when I called the function, I was calling it using the global object and the heap object. So I copied an object from the global area and I copied an object from the heap. These two objects got copied into the stack. Okay, and then any changes that are made here are not going to have any effect on this one or have any effect on this one because I make copies of them. Okay, all right, and then let's do another example. Let this one return. Okay. Now F2 is a slightly different function. F2, see, F took struts as its input. So that means it takes copies of them. F2 takes pointers to struts. F2 acts like Java. See, by making F2 take pointers to struts, I'm making F2 act like Java's reference variables. So F2 is going to be very much like it's going to act very much like the Java version of F, because it's going to be taking references or pointers. Okay, so now I start here by saying call F2 with the address of S1. Okay, S1 is up here. It's got an address in memory. So I'm going to make F point at this guy. S4 is an address because S4 is a pointer. See, S4 is a pointer, so I don't say take the address of S4. If I put a little address thing in front of this S4, the program would be messed up. Okay, see, S4 is an address. S1 is an object. Since S1 is an object, I need the address of it. Since S4 is an address, I can just pass it to F2. Okay, so now here's F2. Now notice its parameters haven't been initialized yet. Now they're initialized. One points to this guy in the global area, and 1 points to this guy in the heap. Now these guys are in out parameters. Now they're out parameters because now F2, if it wanted to, can reach inside there, make a change. And F2 can reach inside there and make a change. So in C, if my functions take pointers to objects, then they can be acting like out parameters. Okay. When the function took struts, struts are copied, so they're inherently in parameters only. Okay. If I write my function to take pointers to struts, then they can become in out parameters because I can, just like Java. Now they're acting like Java does. Okay. So F2 is more like Java's F. Okay. Even though it's, see, F in Java is written more like F in C, but C's default is to copy these. If you want C to act like Java, you have to say pass by pointer, pass by pointer. In Java, everything is automatically reference. You're automatically passing by reference. That's just, you can't do it any other way in Java. You have to pass by reference. Okay. Okay. So in C, I can write two versions of this function. One that's passed by pointer and one that's passed by copy. This pass by copy is often called pass by value. Okay, because you actually have the value of S1. It's just a term of art. We call it pass by value, and you should think of pass by value as a synonym for pass by copy. Okay, this is pass by pointer, so you get the address of the thing you're working with. So you have the address of it, so you could look inside of it. You're past the address of the original thing, not a copy of it. Okay. This one gives you a copy of the original parameter. This gives you a pointer to the original parameter. Okay. All right. So C and Java act differently. Now, to make things more confusing is that arrays in C act like objects in Java. So let's go and do another example. And this is one of the reasons why C is kind of a mess to work with. If I do the same program with arrays in C, it doesn't act the same way. Okay. Now in Java, arrays are objects. So the Java program really wouldn't matter if I turned this from a strut to an array. Okay. If I change these guys to array parameters and an array parameter and call this function with two array parameters, if I redefine the function to take two array parameters, not much changes. Arrays are just objects. Okay. So the syntax will change because it's arrays instead of objects, but they still will be out parameters. They'll still be references to the arrays. Okay. But in C, when I switch from struts to arrays, things change a lot. Okay. All right. So here's a global array. Here's a function that takes in 1, 2. Well, I wrote it to be a little bit different. I wrote it to take in 4 arrays. Okay. No, so it takes in array N1. Okay. It takes in 2 arrays. There's one array and there's another array. First of all, in C, arrays never know how big they are. So for this function to know how big that array is, it has to have an int parameter saying how big the array is. In Java, arrays know how big they are. In C, they don't. So here I'm passing the array and how big it is. And here I'm passing the array and how big it is. And see the 5 in there? That's not an array of size 5. C, for whatever strange reason, lets you put a number in there and it ignores it. Okay, that's not an array of size 5. That's just a you read that as a reference to an array. Okay, and then this, you have to say how big the array is. This is a reference to an array. I could put any number I want in there and it'll be ignored. Okay, in fact, what you're supposed to do is leave those brackets empty. You should leave them empty, but C doesn't require you to. C lets you do this, but then it ignores those numbers, which can be confusing to beginners because those numbers mean something. Like here, suppose I put the number 10 there. that changes the meaning of this. Okay. What does this line of code do?
It initializes the array.
How big is the array?
5,
Why?
because you have 5 numbers in it.
Yeah, but I didn't put anything here, right?
Right.
What does that do?
Does it fill the remaining 5 with null or 0?
Yeah, it actually creates an array of size 10 and only initializes half of it. Okay, so what does this do? Think of it. How would you explain this in words? Since there's no number here,
So is it not initializing it with 5? With
yeah,
5
it is. So what's interesting, this and that? This does what?
That's not adding additional spaces. That's only, so it's just initializing the numbers that you provided on the right side.
Yeah, it's looking to the right-hand side to see how big the array should be. If you do this, okay, now here's a problem. Suppose you do this.
It's not initialized.
No, it's not. It won't compile.
Oh, okay.
How big should the array be?
Unknown.
Unknown. This is what?
10.
10. What's it initialized to?
10. All null. 10.
No,
10
garbage.
Oh, okay.
Because you didn't say. Yeah, in C you have to say. So this is 10 slots initialized to garbage values. This, since you didn't say how big it is, and there's nothing to initialize it with, it doesn't know what to do. But this is allowed because it ignores, well, what it does is it goes over here to see how big it should be. Here's a real problem.
Assuming it would give some sort of error.
Let's find out. Okay. Now, look what happened. See, that line of code was done by the compiler, right? So what did it do?
Just took the first 3.
It seems so, but in fact, that's not really quite what happened. The 2 and the 1 are sitting there, and they could cause problems. They're actually, the visualizer is showing you is it only did these, but in fact, the 2 and the 1 were made use of. They're sitting there, but they may actually, depending, you can get weird subtle errors in your C programs if the number you put here doesn't agree with the length of what you put over here. If you give an initializer, you should put nothing over here, unless you're going to do like we did a minute ago, which every once in a while some people will do. They'll create the initializer bigger than the data here. Every once in a while people do it that way too. C is a very strange language. It lets you do very weird things. So if you have an initializer, you don't need to put a number there, but then you get the size of the initializer. If you put a number there, that number is how big the array is, and then that beginning of the array gets initialized. And you get a problem if you do something weird, like, and then you put a lot of numbers over here. You could end up with problems now, because you actually are initializing the array to bigger than what it is, and you get an overflow. You get an array overflow, which can cause bugs. Okay, all right. So C is kind of weird. Okay. Okay. Now go back over here. I'm going to make this the right way. Okay. So there's our global variable. Remember, the idea was this empty bracket and this empty bracket don't end up meaning the same thing. This empty bracket means make the array big enough to hold that, the initializer. This empty bracket means I'm a pointer to an array of arbitrary size, and this is going to be how big it is. Here, in fact, if you fill in the bracket here, it gets ignored, because what this is this is a pointer to an array. This is a pointer to an array, and that's not at all clear from how the C language works. These guys are references, pointers. They're not array objects. See over here, that is a strut object. It's in that object is the strut. This thing is not the array. It's a pointer to the array, even though there's no pointer notation used here. It turns out to be a pointer to the array. In the case of struts, if I want a pointer to a strut, I use pointer notation. So that is the strut. That is a pointer to the strut. In the case of arrays, the parameter is a pointer to the array, and you have no choice about that. It's just like Java. In Java, reference variables are pointers, and you have no choice about that. In C, arrays act like Java pointers. That is a reference to the to the array. You have no choice of that. Okay. Then you have to know how big the array is. Okay. So that's actually, and if you don't pass that parameter, then you're kind of stuck, because then you have an array and you don't know how long it is. You'll still, the Java, C doesn't care. If you don't pass this extra parameter, the C language doesn't care, but you're kind of stuck and you can't do anything. You can't iterate through the array because you don't know where it ends. So you need this extra variable to say how long that array is. And you need this extra variable to say how long that array is. Okay. All right. Now let's look at the visualization of it. Okay. So we're going to create the arrays. Okay. Notice the arrays are sitting in memory. Notice that this thing is the array. See, he is the array, just like this thing here is the strut. Whoops. Just like that is the strut and that is the strut. This is the array. See the array sitting in, it's not in the heap. The array sitting there in the local variable. That is the array. Okay. So far, arrays are acting more like struts in C. They're not acting like Java arrays. Okay. But then you get to the function call. Now you get to the function call, and you get pointers to the arrays, like in C. But the arrays are not in the heap. This is tremendously confusing, especially if you've been doing C program or Java programming. Okay. The arrays in C sometimes act like struts and sometimes act like Java objects. Okay. The array is in that guy is the array. He's actually in the local variable. This guy is in the local variable. Okay. But then this thing doesn't copy the array from here into the local variable here. The parameter passing is not a copy now. That's not a copy of the array. That's a pointer to the array. That makes it a what? If this function has a pointer to the array, what can it do? Start thinking like C programmers. If you've got a pointer, if your function has got a pointer to the thing, what can it do?
You can change it.
It can change it. So it's a.
Would that be an in out or just an out?
It's an in out. Yeah, it gets, because it's passing information into the function. And if you wanted to, you can manipulate that data and pass information back out. So it's an in out. Now, in Java, array parameters are always in-out parameters because they're objects, they're references. But notice that in the case of struts, we could have the function be, in the case of struts, that function takes copies of the strut. So that's an in parameter only. That function takes a pointer to the strut, so it makes it an in-out parameter. With arrays, I don't have any choice. The function takes a pointer to the array. I have no choice about that in the C language. But the funny thing is, the arrays don't always act like Java arrays. Like here, the array is not in the heap, the array is in the local variable. So the local, this local variable is kind of like a primitive. It actually holds the array. But this local variable, notice it's declared the same way, int nums2. That's this guy. See the declaration? How it looks a lot like, I should have deleted those 5s. See, that declaration looks a lot like that declaration. But that is the array. That is a pointer to the array. Okay? When it's a function parameter, the array is a pointer. When it's a local variable, the array is the object. The variable is the array. This guy is the array. This guy's a pointer to the array. But the notation is the same notation. So you have to remember to read it real carefully. When you have a local variable, it is the array. When you have a parameter, it's a pointer to the array. Okay? So arrays in C don't act like reference variables in Java. They don't act like struts in C. Okay? Arrays act sometimes like struts in C and sometimes like reference variables in Java. So they're their own thing. Arrays in C are a mixture of C style objects and, I'm sorry, Java style objects and C style struts. Okay, so that means you have to know the rules. You have to just know the rules. When you declare a local variable as an array, the local variable is the array. When you declare a parameter as an array, the parameter is a reference to the array. Okay. In Java, every array variable is a reference to an array because arrays are objects. So you use you use reference variables. But in C, you have a messy situation. Arrays as parameters act one way. Arrays as local variables act a different way. And then we're going to see that arrays as fields in a strut act a third way. Okay, so arrays are a mess in C. They have one way of acting when they're local variables. They have another way of acting when they're parameters. And they have a third way of acting when they are fields inside of a strut. Okay. All right. So we've seen here now that the array variable acts its own way. It acts differently than struts and it acts differently than objects. Okay. Now let's go to the example here. No, let's see. Here, working with struts and strings. Okay, I'm going to close some of these files to want to work on. Okay. Working with struts and working with struts and strings. Okay, I'm going to make a little change. The code's pretty lined up. So the idea is that I want you to be able to see the changes. If you open these two files in an editor, and then you can toggle back and forth between them and see where I made a change. Okay, the big change is this field here, from a char to an array of char. Okay, so inside of the strut, where there used to be a single char, there's now an array of char. The question is, does that guy act more like a local variable or like a parameter? Because remember, we said that when you have a local variable, it actually is the array. When you have a parameter, it's a reference to the array. So when you stick an array inside of a strut, which one does it act like? Does it act like the reference variable or does it act like the local variable? It turns out it acts more like the local variable. That C is the array. That C is the array. Inside of a strut, so the arrays inside struts act more like the arrays that are local variables. Okay, so C is the array. Okay. Then when I make copies of the strut, I'll end up making copies of this array. That's the only time Java will, or that's the only time C will make a copy of an array. See, when you try to pass an array as a parameter, what C doesn't want to do is make a copy of the array. This guy is the array. When you call that function, C says, I'm not going to copy an array because arrays could be billions of items long. So I'm not gonna, this is the motivation was arrays could be billions of items long. So you're not going to want to make a copy of that array. So you just take its address and you pass the address. So this guy is a pointer. Okay. But if the array is inside of a strut, now, even if it's a billion items long, you'll make a copy of it. Okay. When you make a copy of the strut, you have to make a copy of the array inside the strut. Okay. Java doesn't work this way. If you put a string inside of an object, you get a reference to the string. You never get the string. You can't have a string inside of an object. You can't have an array inside of an object. Java only has two kinds of variables, primitives and reference. C's got too many kinds of variables. That's a primitive, so the int's inside the strut. That's a primitive, so the double's inside the strut. This acts kind of like a primitive, so the array is actually inside the strut. Okay, so if you go play with this one, you'll see C make copies of the array, which it won't do when you call a function. When you call a function, C refuses to copy an array, but if you put the array in a strut, then C will copy it. So here's a strut with 1, 2.3, and the string cat. And then this is another strut with the string dog. Okay. And then you start stepping through the code. Okay. We're going to initialize this strut. Now we're going to initialize that strut. And this strut was the global one. So it was built by the compiler before the program started. So that strut was put there by the compiler. Okay, now we're going to initialize this other strut. Okay. The variable is the strut. Noticing it also is the array. The array is right inside of the strut. Okay, that's important. The array is inside the strut. Then when we pass the strut as a parameter to the function, the array gets copied. So that array got copied to there. If this array was a billion items, your program would very slowly copy those billion items to here. And if that array was a trillion items, your program would very slowly copy them here. And this is something that programmers in C have to worry about. They have to be careful about accidentally sticking an array in a strut, because if you're not careful, the strut can get very large and it could slow your program down. If you don't want the array in the strut, how would you avoid that?
Pointer?
Yeah, but then you have to do it yourself. You'd have to explicitly say, I want a pointer to an array in my strut. And then the array isn't in the strut, and then it'd be like Java. You would have a pointer to the array in the strut, and then the array would have to be somewhere else. But you would have to do that. You would have to say, I want a strut with an array, but I don't want the array to be the array itself. I want it to be a pointer to the array. So that when I copy the strut, I copy the pointer, not copying the array itself. That's real big. Usually when people put arrays in struts, they put them in there by pointer, not by value. This is called an array by value. The actual array is in the strut. Usually you would put a pointer to an array inside the strut. Functions do that automatically. In C, when a function takes an array parameter, it by default says, I'm not going to copy the array. I'm going to make that a pointer. So even though you don't use the pointer syntax, the array parameter is a pointer. And it's confusing. But and it makes things tricky when you have to learn how to read C code. So you have to keep remembering that struts can act like primitives or they can act like objects. They default to acting like primitives. If you want to make them act like objects, you have to explicitly say, I want to use a pointer. Arrays are weird. In some places, they act like primitives. In some places, they act like objects, like Java objects. Mainly when you have function parameters. Function parameters, the arrays are always pointers. They're always by default. We say that they decay into pointers. C has its own terminology for this. This array decayed to a pointer. So in here, it's just pointing at the array. It isn't, the array is down here. When we ran the code, the array was somewhere else, and this parameter pointed at the array. And this number is ignored, and this number is ignored, because this thing's a pointer to an array of any possible size. It could be a pointer to an array of size 1 billion, and that's okay. This number would tell you how big that array is. Okay. All right. So when you go to look at C programs, like when you get over here and you start reading C code, you have to keep all these things in mind. Okay. You have to keep in mind that, like, this is a pointer to a string, because strings are arrays, but it's an array of string. Okay. Now it's a pointer to a string, but so that's how you always handle strings. You can only pass strings by passing pointers to them. Okay. On the other hand, this guy's a strut. This guy's a strut, but notice that they want a pointer to the strut. See, they use a pointer. See, the P stands for pointer to strut. Okay, that's because they don't want to copy the strut. The strut can be quite large. They don't want to make a copy of it. So in C programming, they tend to use pointers to struts more often than they actually use the struts themselves. So down here, they're making now that makes these guys in-out parameters. If they use the struts themselves, they would be strictly in parameters. But because they use them as pointers to the struts, and they have to explicitly say pointer, because by default, C would make it the strut itself. So then they become in-out parameters. This one turns out to be only an in parameter. It does not make any changes to that data structure. This one turns out to be an out parameter because it will change that data structure. It'll change the data structure it points to. So you got to you have to keep these pictures in mind when you read the C program. I've said earlier, you should be drawing pictures when you write C programs. Sketch little things in your mind about who's pointing at what. On a piece of scrap paper, when you call a C function, you should kind of like try to force yourself to draw a little sketch of, does that point at something? And if it points at something, where's the something it's pointing at? Is that a copy of something, or is it pointing at something? You look at all your parameters. Is that a copy of something, or is it pointing at something? Is it a copy, or is it pointing? If it's a copy, what's it a copy of? If it's pointing, where is it pointing to? Okay, so from now on, what we're going to do is we're just going to look at the C code. I mean, we're going to start looking at the we're just going to go and look at these examples using C program, C code, and calling create process and all that. And we'll be using all these ideas, but we'll be using them as we look at Windows programs. So we're going to keep writing Windows programs, and lurking in the background of all the Windows programs we're going to be writing is all this stuff about C, okay? And read these examples slowly, just keep rereading and rereading this stuff, especially this chapter here. Read this one on memory management, okay? It's a very good explanation of a lot of these ideas. This all falls under memory management. When you've got copies? When do you have pointers? If you have copies, where were the copies made? All that falls under managing your memory, okay? So read that example carefully and dip into these and keep reviewing them. Especially if you want to be a good if you want to be a good programmer, one of the good things about learning C is it forces you to know Java better. If you can understand C, you'll understand Java better because you'll appreciate the fact that Java is doing memory management for you in many cases. But Java's memory management, a lot of Java programmers forget that it's really there. They just say, oh, Java does so much of it for me, I don't have to worry about it. And that's not true. You do need to worry about Java's memory management. And by learning some C, you get a better appreciation how Java and C# and languages like that are doing a fair amount of memory management for you. And you start appreciating what they're doing for you. And you see when there are problems, even with Java's memory management. Many of the subtle problems with many of the subtle bugs in Java programs turn out to be memory management bugs. And they're hard to find because people tend not to think about memory management in Java. So then they end up with sometimes subtle bugs. Okay, so learning C is a good way to force yourself to get a better appreciation of Java too. Okay, so we should quit there. Anybody have any last second question? These examples, this is not trivial stuff. This is the kind of thing that most people say it takes years to absorb this. You got to start somewhere. Okay, so this is a starting point. It can, many people agree that it takes a long time to really absorb all these subtleties about how arrays and struts and objects and pointers all work. So step through these examples, step through the code and read these pages. Okay, so I'm gonna go ahead and stop there. And on Wednesday, we'll go back and we'll look at the actual homework 2 examples. We'll go back and look at the homework 2 example, the actual code that calls create process. So we'll step our way through this sample code on Wednesday. And then after that, we'll go back to the textbook and we'll just stick, then for a long while, we'll stick with operating systems theory. So after this, we'll go back to the textbook and start talking about operating systems theory. Okay, so see you on Wednesday. Bye.